everyone. We'll wait a few minutes for people to arrive and join. Okay. 17. All right. I think we could probably get started. Okay. Hi, everyone, and welcome to the ASA section on teaching statistics in the health sciences fall webinar. My name is Maria Charleglio, and I'm the chair of the section. We are a section within the American Statistical Association devoted to excellence in teaching statistics and conducting statistics education research in the health sciences. Our goal is to promote communication around these activities to professionals interested in teaching statistics. If you'd like to learn more about our section, I encourage you to visit our website and blog, where we post about different section activities, resource reviews, and member highlights. We have many resources available for statistical educators. If you're looking for real-world data examples to use in your teaching, I urge you to join our section and visit our resources portal, where we have data sets that are free for section members to use. Dr. Lucy D'Agostino McGowan is today's speaker. Lucy is an assistant professor of statistics at Wake Forest University, and she is the 2023 recipient of our section's Young Investigator Award. Today's webinar is being recorded, and the video will be posted to the TSHS website after the session. And now I'll turn it over to Lucy.
Thank you so much. Well, I'm excited to be here and to be talking about these topics. So thank you for inviting me to do so. So today I'm going to be talking about design principles for data analysis. And I think this talk actually fits quite nicely in kind of the mission of this particular section, because it is both tools that we've come up with as teachers ourselves of statistical concepts, and also ones that we've used to sort of help us think about how we are evaluating or doing like research within the education space and statistics. So yeah, so you can find my slides if you're interested at my website at lucymcgowan.com/talk. And I wanted to mention that this work is in collaboration with Stephanie Hicks at Johns Hopkins and Roger Ping at the University of Texas in Austin, as part of a broader set of work that we've been doing in this space that we're calling analytic design theory. So if the topics are interesting to you and you're sort of interested in other work in this area, we have a website, analyticdesigntheory.org, where we've sort of put together lists of different papers that we're either working on, including the ones that I'm going to talk about today, as well as other presentations that we are giving or have given in this area, with some kind of background on our kind of big picture ideas we have for this. So the first part of this talk is going to focus on the work that we published in the Journal of Computational and Graphical Statistics last year under the same title, Design Principles for Data Analysis. So this is work that I did along with Roger and Stephanie as well. So I want to start by talking about, so we have this word design in the title of this talk and of the paper. And so I thought I would sort of spend a little bit of time just going through what do I mean by design. And so to start, I talk about kind of when I think about statistical thinking as sort of this complementary but different idea than design thinking. So historically, or typically, when I think of statistical thinking, I think of this as some process where like you have some data and you apply some process to it, like maybe, depending on what the data is, like what is the form of the data, what's the type of question you're trying to answer, and then you like pick a method based on that. So it's sort of this like convergent thinking where you start with a data set and some types of variables, and you converge on the type of method that you're going to apply. And maybe this will then give you kind of the statistical answer to the question. So kind of along these same lines, maybe you've seen these like in the classroom or elsewhere, but this kind of flow chart like thinking where, maybe you'll start with what type of data is it? Is it continuous or discrete? And you kind of go down this flow chart. Is it normally distributed? How many groups are there? And that will kind of tell you like what type of test you should use, a pair t-test or a t-test or one sample t-test, et cetera. So this is sort of like what I think of when I think of statistical thinking, or at least when I'm describing statistical thinking, I mean sort of like input, data type, output method to apply to this data. And this is very important. So I don't want to minimize the importance of this. In fact, I think most of what we spend our time on pedagogically is this sort of like piece of sort of teaching this kind of flow charting. But I think especially as we're sort of building more and more tools that can handle the flow charting kind of routinized, procedures for analysis, I think that the external pieces to this are becoming more and more important because that's the place where like the humans are actually really necessary. A computer could go through a flow chart and apply kind of different methods according to some algorithm, but a person is needed in order to kind of take into account the design part, which is what I'm going to talk about next. So this is like, I think of statistical thinking as different, but complementary to design thinking. And this is, design thinking is something that people talk about a lot in the engineering space. The model that I'm going to refer to here is one that was proposed by the Institute of Design at Stanford, but there are other types of models, I suppose, that you can do. But this is sort of a typical one when people think of design thinking, where you start with thinking about the end user. So who is it that's going to be consuming whatever this product is? And in our case, that's a data analysis. So who is the audience that this data analysis is for? You start with empathizing with that end user. So thinking about the end user, empathizing with them. And then the next step is defining. So defining like what it is that you're trying to do as part of this process. And then ideating, kind of coming up with how you might go about it. Prototyping, actually creating a prototype. And again, this is sort of the format that kind of people that are building, user interfaces or whatever in some kind of engineering space, this is the language that they use. But I think we can apply a lot of this in the data analysis world as well. And then finally testing. So, taking that prototype and bringing it to the end user and seeing whether it actually did what you thought it would do. And so this whole process is very iterative. So you're sort of throughout, you're kind of going back and forth between each of these different stages. You're testing and then you see that the prototype wasn't exactly what you thought it was. And so you go back to that stage and et cetera. So you're sort of constantly going through this iterative set of different parts of each of these stages in the design thinking. And an important distinction here is that design thinking, as opposed to statistical thinking, is a divergent process. So as opposed to kind of converging on a single method, so it's the opposite, where we're sort of ideating, we're coming up with a bunch of different ways to try to answer this question, and so it's more of a divergent type thinking as opposed to convergent. Okay, so why is it that we're doing that? Why are we thinking about analyses in terms of this design language? And why are we trying to define these principles of a data analysis design? Well, the first reason is that we wanted to be able to provide a common language. So it's hard to talk about these concepts in the context of statistical analysis if we don't have if we don't have words to be able to talk about it to begin with. So as part of this paper, we tried to sort of put into words what we thought the different principles of analysis design are. We came up with 6, and I'm going to show you what they are, but I'm open to the idea that perhaps these are not the only 6, or perhaps they're not the perfect way. We sort of are just trying to get something started with that. And then the next reason why we thought this was useful is to improve pedagogy, so to improve how we're teaching these methods. And that comes under kind of this common language, but it's hard to be able to teach about how we should think about design if we don't actually have any principles written down. So we're sort of trying to improve that by writing down some of these principles. And then the final reason why, and this is going to be kind of the second half of this webinar, I'm going to talk a little bit more about alignment, but the big idea here is that, a major goal, I think, of a data analysis is often data analyses are not conducted in a vacuum. For the most part, they're conducted for a specific consumer or specific audience member. So that could be you yourself, but often it's, a clinician, or it's, maybe someone in your company who is requesting a certain analysis, or maybe it's the general public if you're doing some kind of public health analysis, or maybe it's other people in the field who are going to read your analysis and then determine if they're going to make some kind of actionable change. And so the idea here is that if we can write down the principles of data analysis, then you could sort of improve alignment and expectation between data analysis producers, so the people doing the analysis, and consumers, because we have this shared language that we can use to then be able to sort of align people on expectations across each of these different principles. And I think this is also important because in some sense, the statistical thinking, at least how I've defined it, there is in some ways a right or wrong answer, so there's certain tests, statistical methods that are only appropriate given certain data inputs, for example. But for this design piece, there's really not a right or wrong answer. It does depend on who the audience is and what their expectations are. And so being able to sort of put words to each of these different design principles, and also be able to sort of quantify in some way how an analyst might put certain weight on certain elements or principles, and a different consumer might put different weights, and how to sort of bring them into a negotiation where they can kind of come to an agreement on what those actually should be for a certain analysis, can be important for making sure that analysis is deemed successful. Okay, so here's sort of just a little bit of a schematic on kind of what I mean by that alignment. In theory, you have some producer of data analysis. I think a lot of us here are probably that person. So this is like the data analyst, and they create some analysis product, which then is going to go to a consumer of data analysis. So this would be your audience, whoever you're doing the analysis for, and then they're going to be the ones who, in theory, evaluate kind of that analysis on whether it met their expectations. So this is you. This could be a clinician as the consumer, or it could be another statistician, or it could be the general public. And so the producer as well as the consumer would each have some set of kind of how they would weight different design principles. And the goal is sort of to align these weights between the two. So I'm going to first define what we had came up with as these principles. I'm going to show you a little bit of data when we had some students in the classroom use these principles. And then I'm going to talk a little bit more about what we've been thinking about recently in this alignment space. Okay, so design principles for data analysis. Here's the first one, data matching. So the first one that we defined was data matching. How well does the available data match the data needed to investigate the question? So here's a little schematic that we came up with to sort of describe what we mean by this. But essentially, let's say the question was something like, is there a relationship between ozone levels and mortality? So analysis that would be kind of on the lower end of the data matching scale would be one that only had access to maybe temperature and hospital admissions. So we have like surrogate variables for both the exposure of interest and the outcome. And one that would have higher data matching would be one that actually measured ozone levels and mortality. I think this one's particularly interesting because, so what we mean here is not necessarily what question the analysis is answering, because of course the question the analysis is answering has to match what the data is. But what we mean more is the kind of lofty goal question, the question that sort of is intended to be answered. How well the data matches that question might vary. And the varying degree there, may or may not make the analysis good or bad. For example, it might just be impossible to access the data that would actually precisely answer the question. And so in that case, you might weight this a little bit less for a particular analysis because you didn't want to have to dedicate the resources it would take to actually collect the data to do that. So here's an example where this happened somewhat recently. This is from July of 2021. There was a headline that said, the CDC study shows that 74% of people infected in a Massachusetts COVID outbreak were fully vaccinated. So this is an example where the question that people actually probably care about, so the kind of high level lofty question that people wanted answered, or what most people wanted answered, was what's my probability of infection given I was vaccinated? So what they want is to know, among among all the people vaccinated, what's their probability of getting infected. But what this particular study had access to was the probability of vaccination given that you were infected. And this is this particular issue we saw all over the pandemic, where the data didn't exactly match the question that people were hoping to answer with it. That particular headline did correctly, say what the data provided, but people interpreted it in all different ways. But anyways, this is sort of an example of when a question, the data maybe didn't match exactly what the question that most people had in mind was. And so, but it wasn't necessarily not worth studying. It was, still worth giving this particular information. It just maybe didn't exactly match what the audience was expecting. Okay, here's another example. Another principle. The next one is exhaustive. Are the specific questions addressed using multiple complementary methods, toolings, or workflows? So was it an exhaustive analysis or not? And so here is a kind of schematic again, where one that was more exhaustive, the analyst selected multiple elements to investigate some specific hypothesis, versus one that was less exhaustive, maybe only one, the analyst only selected one element to investigate a specific hypothesis. So here's an example of a study, just to I tried to sort of pepper in some real examples so you could get a sense of what we mean by defining these principles. And again, to sort of show how they're tangential to the actual statistical methods that were implemented. This is sort of thinking about the broader design of these analyses as opposed to what statistics were to calculate the final result. So this was a cohort study that we did. We were looking at the relationship between two different diabetes drugs and the risk of heart failure in a veteran population. And so because this was observational data, but we were trying to draw some causal conclusions, we looked at this in many different ways. And so we first we matched the individuals in this study, so individuals on the different diabetes drugs, and then we looked at what their risk of heart failure was in that matched cohort. But then we also performed a weighted analysis, and we also performed an analysis under different kind of classifications of the exposure status. And the reason we did this was because the people who were investigating this study, or who were going to be consuming the research, would potentially be skeptical of any one of those analyses. And so showing kind of the same type of results under several different methods was useful for the audience. And again, this is an example where in this particular case, that was advantageous for the audience that we were targeting. We were targeting clinicians who were trying to make decisions about whether they should, prescribe these different drugs to particular populations. And we knew that these clinicians, some of them would be very familiar with certain types of methods and some would be familiar with others. And so we wanted to show the similar results across all these methods to kind of further convince that audience of our result. This next one is skeptical, which I think skeptical and exhaustive are very similar, but the skeptical means are multiple related explanations considered using the same data. And so this is similar to the exhaustive, where you might use different methods. Skeptical, I think of as more like, does it include a lot of sensitivity analyses? So not just are you using different tools to answer the question, but are you also considering different angles that could have explained the relationship that you're seeing? And so here you have some data, and maybe you have multiple different ways that you could have explained the result you're seeing. That would be more skeptical, versus just a single way to explain it would be less skeptical. And so some examples of a data analysis that was more skeptical. There's this study that's famous from the air pollution literature. There was this Harvard 6-city study that was looking at the relationship between particulate air pollution and mortality, that showed this very strong linear relationship between cities that had more air pollution, it showed that they had higher mortality. And this was, the result was so strong that they sort of wanted to be sure that it was really the case, that there wasn't some other alternative explanation that could have driven this result that they were missing. And so the Health Effects Institute commissioned this special report in 2000 that was hundreds of pages long, where they basically looked at all the data from every different angle to make sure they weren't missing some important other factor that could have been driving this analysis. So this would be an example of a very skeptical analysis. that was necessary in this case because policy change was going to be put in place based on that initial study. So they wanted to make sure they had done a fully skeptical analysis so that the audience, the policymakers, could then make an appropriate decision. There are other types of studies that are less skeptical. So I think a great example of studies that are less skeptical, but appropriately so, are studies that are pre-registered on clinicaltrials.gov, for example. So lots of clinical trials, they pre-register what they're going to do, what their primary outcome is, how they're going to collect their data, who they're going to collect it from, and how they're going to analyze it. And then they do exactly that. And that's important. And that pre-registration process also kind of removes the necessity of some of that skeptical, and also the randomization removes some of this concern about kind of alternate explanations for an effect you might have seen. And so the goal here is sort of, again, to iterate that these are principles that are not necessarily like positive or negative. They're just meant to be, depending on the audience or the goals of the analysis, you can sort of define how much weight you would put on each of these different principles. All right, the next is second order. So this just says, does the analysis include anything that does not directly address the primary question, but gives important context to the analysis? So here, an analysis that was higher in second order might have several elements that are ancillary to the analysis. So maybe they would have a lot of background text about what the analysis was doing, why certain data was collected, how the data was collected. So for example, data that is collected maybe via a certain type of survey or interview might take a lot of time to describe the process by which people are recruited, the interview questions that they're asked, the way that those interview questions were validated. That would all be kind of ancillary to the actual analysis itself in terms of the numeric analysis. But sometimes under certain circumstances, that ancillary information is important and expected by the audience. So if you were maybe presenting this information for the first time to an audience that would want to know all of that, that would be pertinent. Versus if you were presenting just a report to maybe someone who already had all that information from prior studies that you had done, maybe a study that kind of weighted second order element as less kind of would make more sense. And so again, when we're thinking about these, one of the main drivers for why we sort of set this up was to be able to help analysts think about where they're going to allocate time and have an understanding that you're not always going to allocate time the same way for analysis to analysis. So if I'm presenting an analysis to my boss who has all that second order information, I'm not going to spend hours and hours writing it up every time because I know they already have it. Versus if I'm submitting this to a new journal where that information is really important for the reader, I would spend that time on it. So sort of being able to gauge how you're going to weight these different pieces is important. All right, the next one is clarity. So does the analysis summarize the data in a way that's influential in explaining how the underlying data connects to the conclusions? So this basically just means, is there some really clear kind of explanation of like a single result that you're trying to drive home for the audience? Or is this just a series of, lots of information that, lots of little pieces of information, but not like one point that's getting driven home? And again, this is, some analyses are meant to be like exploratory, where perhaps it would be more on this side of clarity, where you're just looking at things a million different ways. And other analyses are meant to be maybe more confirmatory, where you're focusing in on a specific hypothesis and driving home that point with some kind of element. So an example of a very clear analysis, I think, is this. This is from that same 6-city study that I mentioned before. This study, the original one, had this figure in it that I think really drives home the point that the authors were trying to make. So they were showing the relationship between particulate matter, which is here on the x-axis. So this is like air pollution, and mortality rate. So this is the rate ratio for mortality, and each of these letters is a different city. And so you can see that this is a very strong linear relationship. As you increase the pollution, you are increasing mortality. You've got this strong linear relationship here. And this would be an example of a very clear figure that shows you a very obvious, it drives home the point. And then the final one is reproducible. So could someone who is not the original producer publish the code and data and compute the same results? So a study that was more reproducible, you can reproduce, and less reproducible, you can't. This is the one I think is particularly interesting, because I think a lot of people think of this as the one that's, you should always be highly reproducible. But I do think there are examples. We have a pretty broad definition for analysis. it's possible that like your boss walks in and asks you, they have to make a decision in the next like 30 minutes, and they ask you for, to query a single number. And, maybe that like the process of making that full analysis completely reproducible is not like the time that it would take is not worth it for being relative to the importance of getting them an answer in that constrained amount of time. And so sort of trading off between and like taking into account the reality of time constraints here, I think is part of what we're trying to promote. So at Wake Forest, we had students. I had 54 students in one of my classes across their 8 assignments. They before they completed the assignment, they took each of these 6 principles and they scored them from 1 to 10 on how much weight they thought should be attributed for that particular assignment to that principle. And so just some things that I think were interesting here. We observed between and within person variation of the principles across assignment. And so this sort of gives some sense that there is some variability in these, which is, I think, of interest. That's sort of why we think this is worth studying, because as statisticians, we appreciate variation. So here's just some examples of how the different assignments were ranked. So on the x-axis here is the homework number from 1 to 8, and the y-axis is the principal score from 0 to 10. And I just highlighted 2 students so you could see kind of how they differed and how they ranked each of the different principles. And we also observed variation between principles. And so this suggests that they measure different underlying characteristics of the data analysis, which is also good. If they were just measuring the same thing, then it wouldn't necessarily be worthwhile to have these different 6 pieces. So this is just showing, if we look at the relationship between each of these different principles with each other, we see that there is variability across each of the assignments as well. And then we also had some data from Johns Hopkins. This was a slightly different set of data. We had 15 students there that looked at data analyses done by 2 different analysts, and they were asked to score kind of what they inferred the analyst principles were for each of these analyses. So they basically compared the 2 analyses. The analyses were for the same question and the same data, but they were just done by different people. And so they were supposed to sort of infer how they thought that analyst weighted each of these different principles. And this let us know that the scoring of the principles had some ability to distinguish between analyses done by independent analysts, which again is sort of getting at that variation that we were hoping to. And so this was looking at the principal score difference, which was analysis 1 versus analysis 2 across each of the different principles here. And so we see that there were some differences observed for some of the principles. So that's kind of the first part where I'm telling you about what these principles that we're proposing are. The second part of this talk, I wanted to briefly talk a little bit about what we've been thinking about in terms of alignment. So we've tried to sort of match, now that we have this quantitative way to describe, well, first we have the qualitative, just what these principles are. And then we're sort of stating that you could maybe give some weights to these principles, and maybe an analyst and a consumer might have different weights that they could then kind of negotiate to come to some conclusion. So we've tried to, now that we have something numeric, we've done what statisticians do and turned it into equations, but I'm going to briefly show you a little bit of what we're thinking about in that realm as well. So the idea is that you have, maybe an analyst and a consumer, and the analyst is going to work on a specific analysis for this consumer. And at baseline, they sort of have some weights. Each of them have some way that they would think that for this particular analysis, they should weight these different principles. And then they would have some analytic negotiation where they would have a discussion. So this is like when you meet with, the clinician or whoever you are doing an analysis for, and talk to them about, what their expectations are, what your expectations of the analyst are. And then you would come to some resolution where maybe you'd converge on a little bit on kind of your expectations for the different weights. So I'm going to start by focusing on the analyst here. And this is the model that we've come up with for this. So we're saying that these weights, we're defining this set of weights as some number between, each weight is a number between 0 and 1. So for example, this WI1 would be like the weight for analyst I's allocation to data matching. So that would be like if you had some finite set of a resource like time or something, or effort, how much you would relatively weight to data matching compared to these other to the other pieces of the other 6 principles. And so we assume that all these weights, they sum to 1. So this is like it is a zero-sum game. There's like you have some finite amount of something, so effort or time, and you're trying to figure out what to attribute to each of these different principles. And so we assume this as a Dirichlet distribution. This is just because this is like a way to talk about something that has several different components that each are between 0 and 1 that then sum to 1. And then you could imagine the consumer also has these weights. And so we call those CIJ or CJ rather, 1 to 6. And so the analyst I has these weights 1 to 6, and the consumer J has these weights 1 to 6 as well. All right, so we assume that these weights follow some Dirichlet distribution. These alphas are just concentration parameters from that distribution, such that this this mu I k is going to be the mean of from the Dirichlet distribution for principal k, and so that's just going to be that alpha I divided by the sum of all the alphas, the alpha I 0 there. So that's going to be what we're actually modeling here. So we're trying to sort of set up a kind of theoretical framework. In actuality, you're not going to be like fitting this model. This isn't something you necessarily would have data on, but I think it's useful to sort of map it to some framework that we can, like as statisticians, think through numerically. So that mu I k, that's the mean weight for principal k. So for example, for data matching, that would be like the average weight that I, as the analyst, I would give to data matching for this particular analysis. And then it's going to be compared, it's going to be relative to some baseline principal b. So we're going to take the log of this ratio between these two. And then we're saying that that is equal to this equation here, where this lambda is some field-specific mean. So this is like, I come from the causal inference field, and because of being as part of that field, and maybe actually I'm from the causal inference field and I specialize in diabetes, EHR type records. And so because I'm from this subspecialty, this is like the field specific mean that I often would attribute to for this particular weight K, for this particular principal K. And then this delta I, this is the analyst specific deviation from the field specific mean. So this is like, so I have some field specific mean that I, based on kind of where my training was or where I sit within the field. And then as an individual, I have some deviation from that. We assume that this deviation is, maybe centered at 0. The expectation is centered at 0, but that maybe an individual, you might have a little bit of a deviation. And then we allow for a vector of analysis specific resources. So maybe there's things like budget and time that influence how much you would weight different principles. You would also have this vector of coefficients that indicate how each resource is related to the up or down weighting of principal K. And so this set of 3 parameters here, this lambda, delta, and the x betas, this refers to what the analyst's weight would be at baseline. So how they would weight a particular, a particular principle compared to the baseline principle at baseline. And then we have this phi I here, which is the impact of the analyst consumer analytic negotiation. So this is like an indicator that you're in that resolution stage. So this is going to tell you kind of how much that analyst changes from baseline after talking to the consumer. And so in this picture, the way I've drawn it here, that's what this parameter is here, which shows like a little bit of a deviation after the analytic negotiation. The analyst might change their relative weights a little bit, and that's what that parameter would be. All right, so now for the consumer, they have the same model. It just is going to have different parameters. So now this is the consumer's field-specific mean. This is the consumer's deviation, and this is their set of resources that they might have and how they would attribute those. So altogether, these 3 parameters contribute to their baseline, how they would weight the principal K relative to baseline principal at baseline prior to having an analytic negotiation. And then this theta j, this is going to be the parameter that explains how after negotiation, the kind of delta between where the consumer was and where the consumer is after negotiation. So that change is going to be that theta parameter. So we can call this like Bij. This is sort of the baseline difference. So before doing any kind of analytic negotiation, this is the difference that we would expect between these different individuals. So here, this is going to be the difference in field specific mean. And what this shows, I think sort of putting it in these terms helps to put into like words why what we kind of know is true is true. So if you're in the same field, so if I am used to doing data analyses in, like diabetes research within electronic health records, and that's where the consumer is as well, then our field specific means will be the same, and that's going to make our baseline kind of closer, and because this would be 0 since these would be the same if we're in the same field. So there's the field specific difference. This is the difference between my individual, the analyst's individual deviation from the field, as well as the consumer's deviation from the field, which in expectation should be 0, since both of those should be 0 in expectation, but in any given interaction could be non-zero. And then these are going to be those differences in how different resources are, the expectation for what the resources are, as well as how they affect the weights. And so this can be minimized by if you kind of at baseline agree upon what the resources, what the time and the budget, et cetera, are, that can at least get that X and Z to be the same, which can then kind of improve the delta here. So this distance at baseline between the analyst and consumer, this is that Bij for principal K. And then we define Dij as just the difference between the baseline plus those parameters that happen post-resolution. So that's going to be this distance over here, kind of where you land. And so this is kind of nice because then we can put some kind of like terminology to this. Like we could talk about strong pairwise alignment if we had, some distance between consumer and producer after resolution. If we said that the maximum of that was less than some epsilon, then there was strong pairwise alignment between the two. We could also define other quantities like weak pairwise alignment. We could define potential pairwise alignment. So basically the expectation of this Dij. And recall that we dropped the individual difference from the field-specific mean since we expect those to be 0. So this kind of gives a nice way to think about potentially how well you could be aligned, which also lets you sort of think about how we could improve it. So this is sort of bringing it out of the math and back into the practical for why we're doing all of this. But this kind of gives a better sense to folks about kind of why certain choices might be made when we're trying to do a particular analysis. So for example, one way to improve that potential pairwise alignment would be to choose an analyst from your field. So if you're choosing someone in the same field, then this would be brought to 0. And another would be to agree on the resources dedicated to the analysis. And so that would bring this portion closer together. And then finally, these pieces, both of these parameters occur when you've had a discussion between the analyst and consumer. And in theory, if the discussion goes well, then those can be minimized as well. Okay, so that's sort of all I had. Just in summary, we had defined these 6 principles of data analysis. So data matching, exhaustive, skeptical, second order, clarity, and reproducible. And then we've defined we've used these to help us think about alignment between producers and consumers of analyses, where we can sort of turn that into something that we can think about as statisticians mathematically, which then we can think about sort of improving alignment between the person doing the analysis and the person consuming the analysis across these different principles. So I'm happy to take any questions that anybody might have. You can either put them in the Q&A, or I don't know if there's another way for them to get moderated, but I'm also, if you would like the slides again, you can find them on my website at lucyMcGowan.com/talk. And if you would like to know more about what we're doing in this space, you can go to analyticdesigntheory.org. Thank you very much.
Great. Well, thank you so much, Lucy. That was a great talk. It gives us a lot to think about, and I really enjoyed this different perspective. Um, so the session has been recorded, and as soon as the recording is available, it will be posted on our website. If you aren't a TSHS section member yet, please visit our website, our blog, our resources portal to see the resources that we have available to members, and please consider joining. We'd love to have you be part of our section. So we'll leave it open for questions right now. If not, then we can wrap up, but we'll give it a few minutes for any questions.
I see one in the Q&A.
Great.
Someone was asking if we have resources or suggestions for teaching these principles in interlevel classes. And that's a great question. I have several, all of my classes, my resources for my classes are all publicly available on my website. And I teach this in both my intro to regression and data science class, as well as I teach a capstone class for a math business major, and we do this as well. So you can find those on my website under teaching. And in general, I basically go through pretty similar to what I did at the beginning, where I just define what the principles are. The only thing I add when I'm doing it in a classroom setting is then between defining each of those 6 principles, I do an exercise where I have the students at the beginning of class, they describe a data analysis that either they've read about or that they've conducted themselves, and they put it in like a little speech bubble in a Google slide. And then I have a separate slide for each of the principles, and they stick their little bubble, like where they think kind of on a spectrum that particular analysis fell. And then we talk a little bit about it just to kind of give them a chance to make concrete these ideas as I'm teaching them. So that's the way that I do it. I'm sure there are other ways to do it as well, but it's a good question. Let's see. Someone else asked, can you tell us how do you arrive to this need to use design principles to think about the activity of data analysis? I'm not sure I understand exactly what is meant by that, about the activity of data analysis. Do you mind describing what you mean a little bit more? Oh, like the crafts and yeah. So I guess part of it was it felt like there was a lot of literature on thinking about like the statistical piece. So how do you make sure you're doing the right kind of statistics? But it didn't feel like there was very much literature on how to actually design all these other aspects of a data analysis. And some of this actually, the origination of it was, so Roger and Stephanie have been working on this for a long time. Roger Pang along with Jeff Leake and Brian Caffo, ran these really, really large Coursera classes on data science. They had one of the first ones they made was on data analysis. And they had this final project as part of what they put together for this class. And I think they thought that they would get like maybe a couple hundred people to sign up for this class. And then they ended up getting like 100,000 people to sign up for this class. And they had to then come up with a way, they couldn't grade 100,000 projects. So they had to come up with a way to evaluate data analysis. And they found very quickly that it's pretty challenging to come up with criteria for evaluating data analyses. And so this sort of drove Roger to start thinking about what are the things that make us evaluate whether data analysis is what we expected. And of course, the piece about were the statistics conducted correctly is almost the easiest piece to evaluate, but a data analysis usually consists of so much more than that. And so being able to kind of put words to it was what initially kind of got them thinking about it. And then I joined on after a couple years as well. And I also thought that, part of it, like when I'm teaching, if I give my students an analysis to do, and then I'm grading it, I found it was very easy for me to, figure out like, okay, I don't like this. This wasn't what I was expecting. But it was harder for me, for my students would then come back and maybe rightfully say something like, that wasn't part of the rubric. I didn't understand that I wasn't supposed to show you 500 million plots, And so having actual kind of language to say like, this is not expected to be an exhaustive analysis where you look at it every different way. You're supposed to really focus on this particular piece. I expected this to be clear, whatever kind of terminology I can now use because they have that language for a specific analysis. And it also allows them to contrast two analyses, so that they can sort of build context for when they're expected to do something for different audiences. So if they're doing an analysis for me as their teacher versus for their boss in their internship, they now kind of have the context that that's maybe not always going to be exactly the same. The amount of detail that I require might be different than the amount of detail that the boss requires. So that was some of the motivation that we had for it. And the question was whether we would expand the ideas into a book. So Roger, Stephanie, and I just had a little mini conference on this. We all got together 2 weeks ago to sort of think about these ideas a little bit more carefully. And we talked about the idea of when the right stage for a book would be. And I do think at some point that there will be the right stage. At this very moment, we're actually trying to get buy-in in the field. And so the current goal is we have this one paper published. The one that I just described about kind of alignment is one that we're just wrapping up to try to submit somewhere. And Stephanie and Roger actually have another paper that they're working on getting out as well. So we're sort of trying to build a little bit of credibility in the peer-reviewed space. And then hopefully once that happens, we'll go back and write it. But we've thought about both pieces, but it feels like in terms of getting buy-in, if we can sort of convince the field that this is something that not just us, but other people think is worthwhile, then writing a book and afterwards would be the kind of right order. But I do think this is something that hopefully we're going to be able to keep writing down and allowing for people to be able to use. The question is whether I have any podcast episodes where I discuss these ideas with Roger. I'm trying to remember. I do have several podcast episodes with Roger, but I don't know if we talk about these ideas. I can't remember when we talk about those. I feel like it's always sort of so I certainly do have episodes with him. I think so. He came on I have a podcast called Casual Inference. He came on that a couple years ago, and I don't think we talked about this when he came on. I went on his podcast last year, and I'm trying to remember. I don't know. We might have talked about this a little bit. I think we did talk about sort of the broad idea, because we may have talked about expectations for data analysis, and some of that falls under this realm. But I'm not sure we talked about the actual principles themselves. It's a good question. Maybe Roger and I can get on at some point. Yes. And so the next, someone said they knew that Roger had a few with Hillary on these ideas. And yeah, Hillary and Roger have talked a lot about just design thinking in general, certainly. And there's some really nice episodes out there. They went through a book a couple years ago that was on design that I thought was really, really good. So yeah, good questions.
Okay, well, if there are no more questions, we can wrap up for the afternoon. Thank you again, Lucy. Thank you to everyone for attending. Again, the webinar recording will be posted as soon as it's available. Please visit Lucy's website for the resources for the slide deck and listen to her podcast. Yes, thanks, Lucy.
Thank you all.
Okay, bye-bye.